തുടങ്ങണോ? അല്ല ഇർഷാദ് സ്റ്റാർട്ട് എന്ന് പറയാം, അപ്പം ഞാൻ സംസാരിച്ചു തുടങ്ങാം. Okay. Good evening, and welcome to the first class of quantum mechanics. Right, it's a series of 5 lectures. This is the first class. Okay. Today we will be discussing the double slit experiment and the algebra of linear vector space. Okay. So we were here to master the concepts, as we said earlier. And quantum mechanics actually is not more difficult than classical mechanics or anything. It's even easier, at least in the in the examination point of view. The problems are even much easier often. Right, you may not have to do so. You can solve many problems just by a conceptual, very deep conceptual understanding of quantum mechanics. Okay, all right, and so in the aim of the first presentation is to get a bird's eye view of quantum mechanics. Right, so yeah, we will get a kind of a global view. We just look at it from the top, understand why we use certain structures or why it's convenient, etc. Right, we will motivate the mathematical framework. So these are the things that we will try to discuss today. And before going into this, we will have a short introduction because we will be using a few terms without really explaining this. We haven't really explained these things before, but I want to keep these things really clear. So, okay. Right. So the first thing is one of the terms that we'll be using very often is system. System is a collection of objects, particles, fields, waves, or whatever. The collection of objects that you want to study. It could be particles, it could be fields, anything. And then another thing that we'll be using is state space. It's a collection of all states, all physical states occupied the system. That's what we call a space of states or state space. Okay. So it's actually a mathematical set. You might be familiar with the word set. Right? So the state space is a mathematical set. And what are the elements of the set? The elements of the set are all the possible states of the system. Right? And another term that we will be using is a dynamical system. It's a system that evolves with time. It's a system that changes with time. And we will have a dynamical law. Right? Once we are considering systems that change with time, we will be interested to know the future of the system given the present, or the past of the system given the present, or generally given the state of the system at any time, we would like to know the state of the system at any other time. And there is an equation that's obeyed by this system or the state that's known as the dynamical law. It's the equation of evolution. Okay. For example, it's a Newton's equation. F is equal to md square x by dt square. That's a differential equation. You can solve it and you can get x of t and v of t or p of t, depending on the way you write it. And finally, we will discuss what we mean by state. Right? So by state, generally what we mean is everything that you need to know with perfect accuracy to predict the future given the dynamical law. Right? Suppose you know the dynamical law to be Newton's equation. What information do you need in order to predict the future of the system or find the state of the system at any other time? This is known as the state of the system. Okay. So I take effort to really clearly define these things because these words have slightly different meanings. Okay, in quantum mechanics and classical mechanics. At least the meanings that we get in our mind are different. We'll start with a peek into classical physics. Classical physics is a set of principles and rules. All right. So classical physics is a set of principles and rules. It's actually an underlying logic. Okay, you have to understand this. By classical mechanics, we mean an underlying logic. It's a logical framework that governs all non-quantum phenomena. Okay, all non-quantum phenomena. Right. So you might wonder why we start quantum mechanics before going to classical physics. Right. The reason, one of the reasons is that quantum mechanics is actually more fundamental. Right. Quantum physics is more fundamental. Nature is fundamentally quantum mechanical, and the classical world can be seen as an approximation. At least we believe it's an approximation of the quantum mechanical laws. The classical laws of motion, the classical equations, the classical physics can be seen as an approximation. All right, when the masses involved are really high, then we need only classical physics. But really fundamental theory, the really fundamental thing is quantum mechanics. All right. So you have to remember that it's an underlying logic. I want to emphasize this point because quantum physics, all right, quantum physics is actually, it's also a set of principles and rules. All right. Quantum physics is also a set of principles and rules. Okay. It's also an underlying logic. I'll just write it here. Quantum mechanics is also, okay, an underlying logic. Underlying logic. It's a different kind of framework. All right. You can study the quantum mechanics, the quantum physics of particles, you can study the quantum physics of fields or whatever system that you are worried about. But the rules, the rules of logic, right, the underlying logic that we use will be different. All right. So classical mechanics is a kind of underlying logic, all right, and quantum mechanics is a different kind of underlying logic. So when we go into from classical mechanics to quantum physics or classical physics to quantum physics, you should make this transition in your mind, right? We are using an entirely different kind of logic, right? And we are going to familiarize ourselves with this particular logic. And fundamental to this quantum mechanical way of thinking is the principle of superposition. Okay, fundamental to the quantum mechanical way of thinking is the principle of superposition. We'll be discussing what we mean by these things. Okay, principle of superposition. Now, classical physics includes Newton's equation, it includes Maxwell's Faraday theory of electromagnetic fields, special and general theory of relativity. These are all built inside this particular underlying logic. Okay, and a simple example is the Newton's equation. Okay. So, in order to solve this, you need, for example, if you write it as F is equal to m d square x by dt square, right? This is a second order differential equation. Once you know the force, you can integrate it, but you have to integrate it twice. So, you will have two integration constants. So, you need two things in order to completely solve this equation. Okay. Once you solve this equation, you will get x of t and p of t, but there are two constants of integration, and this constant of integration is, we usually say, we call it as the initial position and the initial momentum. So, once you have the initial position and initial momentum and you know the forces acting on the system, Newton's equation will tell you exactly what the future is or where the system is going, to where the system is evolving. Right. So, this is what we call the state. Right. State is a set of position and momentum. Right. We can say that state is the definition of state, at least in the Newtonian framework, is the position and momentum. If you know the position and momentum at any time, you can know the position and momentum at any other time using Newton's equation. In other words, if you know the state of the system at any time, you can know the state of the system at any future time by solving Newton's equation. Okay, I hope that's clear. This is what we mean by state. So, specifying the state completely in Newtonian physics means giving the position and momentum of all the particles involved. Right? If you are talking about a composite system, specifying the state completely generally means you have to specify the position and momentum of all the particles in this system. Okay. Now, once we write the state as x comma p, right, this I have written it generally. If it's a single particle in one dimension, you will have just one position, one dimension, one x and p. Right, if the okay, so that's the state. Now, here the state space is known as the phase space. The state space of classical physics or Newtonian equation is known as the phase space. What was state space? State space was the set of all possible states of the system, and by state you mean position and momentum. Okay, so if you take a set of all position and momentum, it's known as the phase space. All right, you might be familiar with this term, phase space. Okay, so if you take a single particle in 3 dimension, okay, in order to specify its position and momentum completely, we talk about a phase space. It has nothing to do with any real space. It's an abstract space, but what are the points in this space labeled by? The points in this space are labeled by position and momentum. So, if you take a single particle in 3 dimensions, you will need 3 coordinates to completely specify the position. You will need 3 numbers to completely specify the momentum. Right? So, altogether the phase space would be 6 dimensions. Okay. So, here phase space is the state space of a classical mechanical system. I hope that's clear. Now, we are ready to move on to quantum mechanics. So, you have to understand that quantum mechanics arose out of observations which showed subtle discrepancies between actual behavior of the world and descriptions of classical physics. So the thing is, people started doing experiments. People thought that physics is complete with classical mechanics. All right, we just have to use the underlying logic of classical mechanics to different problems. If you are talking about subatomic particles, just use the underlying logic and see how things work. Right? But once they started applying the laws of classical mechanics or this fundamental logic to subatomic particles like electrons, okay, or protons, or generally atoms, subatomic particles. In the subatomic world, the rules of classical mechanics gave different predictions from what was actually observed. Okay. So there were observations which were not consistent with classical mechanics. This is the reason why we have quantum mechanics. Right. So quantum mechanics is a mathematical framework. It's a mathematical framework which was built, okay, mathematical framework built to describe observations. Okay. Otherwise, no one would have thought of any theory like this. So quantum mechanics was forced upon us by all these experimental observations, okay, or experimental results. So there were so many observations, so much data was accumulated which could not make sense in the classical mechanics framework. Right? And people started trying to construct theories, and there were two successful theories in the beginning. One is known as matrix mechanics due to Heisenberg. Okay, matrix mechanics was due to Heisenberg, and there was wave mechanics due to Schrödinger. Right? So initially they looked entirely different. The way Heisenberg wrote his equations looked entirely different from the way Schrödinger wrote his equations. Okay? And it was Dirac who actually showed, who actually gave a unified framework. He showed that these are actually two different representations of the same underlying theory. Okay. So Dirac understood matrix mechanics and wave mechanics as two representations of the same underlying theory, and it's that underlying theory that we are going to study first, right? Because that's logically more beautiful. We can study this underlying theory of which matrix mechanics and wave mechanics are representations. Okay, that's what we'll be doing first. So the way I explain things, so this was just an introduction to quantum mechanics, and the way I explain things are not historical, right? This is not the way in which quantum mechanics was developed historically. It's not historical. Although if you need a really good understanding of quantum mechanics, if you are interested in it, it's a good thing to go to the history of it, right? How certain ideas came and how people argued, how Einstein came up with objections. These are all really interesting stories, but it will take a lot of time. So our approach would be semi-logical, right? Semi-logical. So I'll try to motivate the mathematical framework of quantum mechanics by looking at a thought experiment. Okay, that's what we'll do. Thought experiment. So we'll talk about a thought experiment that tells us how electrons behave actually in nature, right? Or how electron behaves in experiments, and then we'll pretend that we are constructing a mathematical framework that describes this kind of behavior. Okay, and the thought experiment that I just mentioned is known as the double slit experiment. It's known as the double slit experiment. We'll shortly call it as DSE. Okay. Now there were so many surprising experimental observations, and we'll summarize it just by this thought experiment called double slit experiment. All right. And in the double slit experiment, we will observe how the electron behaves in experiments. Okay. And we will see how the electron behaves. We don't know why the electron behaves like that, but once we know how the electron behaves, we'll try to construct a mathematical framework. Okay. And one more thing which we won't come back to until later in this series. Okay. So there are different interpretations of the mathematics of quantum mechanics. Quantum mechanics is a well-developed, okay, and well-tested mathematical framework. Okay, mathematical framework or mathematical theory. All right, it's a well-developed and well-tested mathematical theory, but nobody knows what it actually says about nature. Okay, we can make predictions, and these predictions are correct, but what does it actually say about the electron? This is not really clear. We don't have this problem of interpretation in classical mechanics. It's very clear what this equation, Newton's equation, means, for example. Okay. And there are different interpretations, you have to be aware of this, okay. And I will be for the purpose of this talk, I will be using a particular interpretation. So when I talk about these things, I will be, in my mind, I will be assuming a particular interpretation. Okay, I will be assuming a particular interpretation, but you don't have to worry about it. Once we go to the mathematics, in the end, in one of the future lectures, we will discuss all these interpretations. All right, we can even examine this interpretation if you want. This interpretation I will call as the literal interpretation. Okay, this is just a term, literal interpretation, which means that I am assuming that quantum mechanics, the mathematics of quantum mechanics, literally describes the behavior of nature. Okay, so there is no different interpretation. We will take the mathematics literally. Right? That's the thing that we will be doing. Now we are ready to go into the double slit experiment. It's a very interesting experiment. The experimental setup is rather simple. You have got an arrangement with two slits. We'll call this as S2 and this as S1. We have got two slits. Okay, and we also need a screen. This is a screen. The screen and this double slits all must be chosen appropriately, but we won't worry about the experimental details here because it's a thought experiment. Okay, so don't worry about the experimental details. So first we will do the double slit experiment using a machine gun. Right? So if you just shoot a bullet at the wall, you know that it will make a hole on the wall. Right? Now you are between the wall and your machine gun, you are keeping a double slit arrangement. Now you are sending bullets through the double slit arrangement, and each bullet will make a hole on the wall. Okay, and as time goes on, if you do it sufficient number of times, if you shoot sufficient number of times, you will see a pattern like this. Right? So behind slit 1, there will be all the bullets which passed through slit. So behind slit 2, you will have all the bullets which passed through slit 2, and behind slit 1, you will have all the bullets which passed through slit 1. Okay, so behind slit 1, you will have all the bullets that passed through slit 1. Okay, so bullets passing through here will reach here, and bullets passing through here will reach here. Nothing surprising. Okay, this is the pattern that you expect. Okay, this is all fine, but now we are going to do this double slit experiment using electrons. Okay, the next thing we are going to do is the double slit experiment using electrons. Okay. Alright, first I need to clarify, we don't know what electrons are. They are really microscopic. We haven't seen electrons. Okay, so we don't know what electrons are. Okay. So we are trying to understand what electrons are based on their behavior. Okay. So first we'll send an electron to the screen. Okay, this is the screen, cross section of this. So you just send one electron to the screen. So the screen we choose appropriately. Okay, I won't go into the details of what kind of screen we are using. We have a screen such that when an electron falls on it, it makes a spot. Okay, every electron falling creates a spot on the screen. Okay, so electron behaves just like a particle. You see a particle which hits the screen makes a spot on it, just like a bullet hits the wall and makes a hole on it. Right? So electron creates a spot on the screen. We choose the screen in that way. Okay, this is exaggerated. Right? And this is a cartoon. Right? What we draw here is a cartoon. It's just for the representation of what's actually happening. Okay, now we know this, how electron interacts with the screen. It interacts like a particle. It creates a spot. That's fine. Now what we do is that we keep the double slit arrangement first with only slit 1 open. Right? We'll keep slit 1 open and send electrons through it. This is an electron beam gun. Okay, it's a very advanced kind of electron gun, which we can manipulate as we wish. So we are sending electron to this single slit. Okay? And as expected, you see a pattern behind slit 1. Nothing surprising there. Alright. So if you are careful enough, you will see surprising things there. But just for the time being, let's assume this is the kind of pattern that we see. Okay. So we are making some approximations here. Don't worry about this for the effect for dramatic effects. Alright. And there are other problems in this pattern itself, which are not really visible immediately. Alright. So at first sight, this is the kind of pattern that we get behind screen 1, and this is the kind of pattern you get behind screen 2. And we explain it very easily because the electrons passing through slit 1 will make spots on here, and the spots will build up to this pattern eventually. This is what we expect. Okay. Now we continue the experiment with both slits open. Right? And what we expect is this, just like the machine gun thing. right? Because we expect that the electrons seem like particles because they make spots on the screen, just single spots on the screen. Okay, so we expect that the electron passing through this slit will make a pattern like this, and the electron passing through this slit make a pattern there. This is what we expect, just like a machine gun. But what actually happens is a bit surprising. This is the kind of thing we get. Okay, this is the kind of thing that we actually get, not this, not for electrons. Okay, not this for electrons, but we get this, and this pattern resembles an interference pattern. You might be familiar with the experiments with light beam, but you don't worry about it. We'll call this as an interference pattern. Interference pattern. Okay. If you are not familiar with interference, don't worry. Just consider it as a name for this kind of pattern, as opposed to this. Okay. So you see that there are points where the electrons does not fall. There are points where electrons fall. Okay. Now you need to explain this interference pattern. Okay. So far we saw a cartoon. Let's just make it a little bit more clear with this probability plot. Okay. So here, instead of the actual picture on the screen, we are drawing the probability plot, which means that at each point the height of this curve gives the number of electrons that has fallen here on this point of screen divided by the total number of electrons. Okay. The height of this curve at this point represents the number of electrons that has fallen here divided by the total electrons that has been sent from the electron gun. Is this clear? I hope this is clear. Okay. And here we call this as slit 2 and this as slit 1. Okay. So this is the pattern that you will get if only slit 2 is open, or only if only this slit is open. If this is the only slit that's open, this is the probability pattern you will get. Nothing surprising. This is what we mean by probability, right? Because it's the fraction. Okay. It's the fraction of all the electrons that reached this point out of the total number of electrons. This is what we call the probability. So this peak gives you actually the probability that an electron will fall at this point. This is the experimental probability, right? This is the experimental probability. Okay. Experimental probability, because suppose you count all the electrons that has fallen at this point and divide it by the total number of electrons, then you get the experimental probability or the measured probability. Similarly, this is the probability pattern behind this slit. Okay, but when both slits are open, you see that you get a different kind of pattern. All right, you don't get this. You don't get just a normal sum of these two patterns. No, this is what we expect. This is what we would get for a machine gun, but that's not what we get. We get this kinds of weird probability plot. Okay, I'll call this weird. Okay, it's actually weird. The thing is that, the important thing is that if, for example, you take this point, okay, these points are of 0 probability. Okay, the low point of this probability plot, these are points where there are no electrons. Okay, but if you see the same point on the screen with only one slit, you see that there were electrons here. Am I right? Similarly, there were electrons here when slit 1 was open. Okay, take this point. Okay. When slit 2 are open, that number of electrons that has fallen here is 0, but when slit 1 was open, there were electrons that actually fell at this point. Alright. So the electron seems to behave differently depending on whether you have opened one slit or both slits. I hope this point is clear. Okay. So the dramatic thing is that the points of 0 intensity, or the points where there are no electron, for example this point, okay, no electron when both slits are open. Both slits are open. There are no electrons here when both slits are open. But if you look, if only slit 1 was open, there were some electrons here. Okay. Some electrons reached here. We are talking about the same point in the screen, all right? When only one slit was open. Okay, I hope this is clear. Now we try to explain this. How do we explain this behavior? And this is what's actually happening. I'll show you an animated image of this. This is what's actually happening. All right. So the electrons come through both slits, and so the electrons coming through both slits. Actually, this is the kind of interference. This is the way the interference pattern is actually built up. Okay. See, you see the spots, all these spots build up, and in the end you see that you get a nice interference pattern. Okay, that's a picture of it. Alright, now what's the first explanation that comes to your mind? Okay, you see that there is interference, electrons interfere. Okay, let's just make a hypothesis. Electrons show interference, electrons interfere. But with what? What does the electron interfere with? Okay, interfere with what? Okay. The first thing that comes to your mind is maybe there are electrons which pass through slit 1, there are electrons which pass through slit 2, maybe these electrons interfere with each other. Okay, we can think of that hypothesis. Alright, maybe electrons, different electrons, okay, maybe different electrons passing through S1 and S2 interfere. Okay, this is a possibility. Maybe they interact and somehow the interference pattern appears. But this can be easily tested. All right, this hypothesis can be easily. It would be fine. It would be nice if this was the case. All right, it would be easy to explain if this was the case. But this can be checked easily. All right, what do? You send just one electron at a time. Okay, you just send one electron at a time, and only after that electron has hit the screen and made a spot, you send the second electron. Okay, and that also hits on the screen, and after that you send the third electron. So you send electrons one by one, one at a time. Okay, but if you do this for sufficiently long time, in the end again you see the same pattern. You get the same pattern even with single electrons. All right, so that's what I have said here. Same pattern is obtained when electrons are sent one at a time. Okay, same pattern is obtained when electrons are sent one at a time. Okay. So the pattern is not caused by interference of different electrons. All right. Okay, and now the pattern is, so if you look at just one electron reaching the screen, you don't see any interference pattern. It's just one spot on the screen. Okay, but this interference pattern is made up of individual spots. This interference pattern is made up of individual spots on the screen. Right? This is how electrons behave. We don't know why. Okay. So each electron makes a spot on the screen. All right. And the interesting thing again is here, the pattern made of single electrons with one slit open, okay, is different from pattern made of electrons with both slits are open. Okay. Now how do you explain this? Okay. Now we ask this following question. It's usually asked in this way. How does the electron know whether a single slit or both slits are open? Okay. That's $1 million question. But this "no" I have put in quotes because electrons really don't have any consciousness. We just say it, all right, for the effect of it. How does the electron actually know whether a single slit is open or both slits are open? Because if a single slit is open, the electron can fall here. Okay, but if both slits are open, the electron never reaches here, the single electron, right? That's what's happening. This is just an example, right? We have got the interference pattern. If only slit, we block this. Okay, if only slit 1 is open, let's say the electron reaches this point. Okay, and you do the same experiment with both slits open, and you see that the electron never reaches here. That's an example. There are points where the electrons reach, and there are points where electrons do not reach. So how does the electron know whether both slits are open or whether only one slit is open? Okay. Now, how does the interference pattern form when one electron is sent through the slits at a time? Right? How is the interference pattern formed? Again, the question: what does the electron interfere with? Okay. There is an interference pattern. So the question is, what does the electron interfere with? Okay. Now we play around with so many possible answers that we can think of, and we come to a conclusion that each electron interferes with itself, whatever that means. All right. We have to conclude that each electron actually interferes with itself. Okay. There is no other way this can happen. So each electron interferes with itself. All right. Another possibility to think is that the electron actually splits into two. Okay. And then somehow rejoins, but this is very costly hypothesis, all right, because if you have, for example, 3 slits, all right, then again you will have an interference pattern, and then you will have to imagine that electron is split into 3. If you have infinite slits, okay, or near infinite slits, you will have to imagine that electron actually is divided into infinite pieces. So this is not possible because electrons always appears as a single whole. Okay, in all the experiments, electron appears as a single entity and never as a fraction, right? So we don't have to imagine that electron actually splits or something. We just have to assume that each electron interferes with itself. How does this happen? For this to happen, each electron, every single electron passes through both slits at the same time. Okay, so this is the conclusion we come by looking at the interference pattern. All right. In other words, we have to conclude that the electron, every single electron, okay, single electron is in slit 1 and slit 2 at the same time, and then it interferes with itself. Okay. Now, this above proposition, okay, this is the proposition that worked. It's known as the principle of superposition. Okay. Superposition is not any kind of position, it's another word. Okay, superposition. It could be, you can do any different experiments, all right. You can do experiment involving spin, experiment involving polarization, and in all these cases you will see that the electron actually seems to exist in more than one state at the same time. And you may not understand this, it's not very intuitively clear, but mathematically there is no problem. Okay. See, for example, if you take a coin or something, classical object, when I say that the coin is here, it means that it's not anywhere else. Am I right? When I say that a coin is here, it means that it's not anywhere else. Okay. But in the case of electron, you cannot say that. The electron can be in slit 1 and slit 2 at the same time. We are talking about the same electron, not different electrons. The same electron can be at two places at the same time. The same electron can be at different places at the same time. The same electron can be everywhere at the same time. This is allowed in quantum mechanics, and this is the conclusion that's forced upon us by nature. Okay, this is forced upon us. This is forced upon us by nature. Okay, we have no choice here, and this is not just about position. If you look at different energy, or different possible energies of electron, you will see that electron can exist in different energy levels at the same time. A single electron. Okay. A single electron can exist in different momentum states at the same time. A single electron can exist in different spin states at the same time. Okay. This is the only way we can make sense of the double slit experiment or all the subatomic experiments. So people tried to avoid this conclusion, but they saw that this is the only consistent way in which we can formulate the theory of subatomic particles. Okay. So this is what we call as the principle of superposition. We'll formalize it a little bit. Okay. So the principle of superposition that we concluded from experiment, all right, this we got from experiment, from the double slit experiment, that the electron actually exists in two places at the same time. Okay. The principle of superposition, we can take it as a postulate, and we will say that the quantum state of a system is a superposition of all possible states. Right. The quantum state could be a position state, it could be an energy state, momentum state, or polarization. All the experiments point to this fact. The quantum state of a system is in a superposition of all its possible states. So if there are possible states S1 and S2, it can be, if there are possible states S1 and S2, it can be in a state called S1 plus S2. This is what we mean by superposition, being at two states at the same time. Okay. Now, principle of superposition is fundamental to quantum mechanics. It's purely quantum mechanical. There's no such thing in classical mechanics. Okay. Now, all weirdness of quantum mechanics can be traced back to superposition. Okay. Now, we can write it as an equation if you like. Okay. So, we don't know exactly how to describe a state. So, we'll use this notation for a state. Okay. By this notation, this angled bracket, what I mean is that we are talking about the state of the electron. Right. So, the electron inside the angled bracket means the state of the electron. We don't know what objects these are, all right. State of an electron. We just need a notation to describe the state of an electron. Okay. We still don't know, we don't yet know how to describe the state mathematically, but for the time being, we'll choose a notation like this to describe the state of the electron. So, this means it's a state of being in slit 1, this means it's a state of being in slit 2. Okay. So, in double slit experiment, we have electrons at two positions at the same time, and other experiments show that this is the case for other measurable quantities like energy, momentum, polarization, spin, etc. Okay. All right. Now, we said that principle of superposition is one thing, that's forced upon by nature. So our mathematical theory, the mathematical framework, okay, when we construct the mathematical framework, it has to include this fact. Okay, it should take into account of this experimental fact that the electron can exist in different positions at the same time. So this is one requisite for our mathematical framework. Okay, I hope this is clear. We saw that electron can exist in two different positions. So when we create a mathematical framework, we should have something corresponding to electron being at two positions at the same time, or two different states at the same time, or a number of different states at the same time. Okay, I'll just repeat it. When we construct the mathematical framework, okay, it should involve, okay, something corresponding to, we are taking this as a reality, okay, corresponding to an electron being in different states at the same time. Okay. So this is one of the ingredient. The principle of superposition is one ingredient of our mathematical framework that we have to construct. Okay. Now I made a grand claim that each electron passes through both slits at the same time. Okay, this is a very grand claim. It's a grand claim. You can test it. Okay, you can actually test it. How do you test? You just put cameras behind slit 1 and slit 2. So this camera can detect electron passing through this slit, and this camera is equipped so that it can detect electrons passing through this slit. Okay, that's simple as that. By camera we don't mean an actual camera. It's some kind of apparatus which can actually measure the electron. All right, it could be a particle detector which is equipped to see whether the electron has actually passed through slit 1. Okay, so we said that electron actually passes through slit 1 and slit 2 at the same time. So we put two cameras here, and we see if the electron is registered in this camera, we know that it passed through this slit. If the electron is registered in this camera, we know that it passed through this slit. That's our arrangement. Okay, so what do we expect here? We already said that the electron is in slit 1 and slit 2 at the same time. So we expect to see the electron registered in this camera as well as this camera. That's what we expect. Okay, at least because we made a nice hypothesis. Okay. So our aim is to observe the electron actually at two places. Okay, but then the result is interesting. We see electron either in this camera or in this camera. It's never registered in both cameras. All right. So the result is that each electron is always found in either in slit 1 or in slit 2, never in both slits simultaneously. Okay, never in both slits simultaneously. Okay, this is the result. Now this is another problem that we have. It's even problematic than the principle of superposition. Okay, never in both slits. Alright, now this is the thing. So does this mean that the electron does not pass through both slits at the same time? Do we need to discard our earlier hypothesis that electron actually passes through both slits at the same time? The answer is no, because when you actually keep this camera here and see that electron either passed through slit 1 or through slit 2, you see that there is no interference pattern. No interference pattern. Okay, so if the electron passes through both slits, you will get an interference pattern. All right, but when you detect the electron, when you try to understand which slit the electron passed through, then there is no interference pattern. The interference pattern is lost. Okay, this is what is happening. So this is the double slit experiment. Without the camera, you get an interference pattern here without the camera, and this is the double slit experiment with the camera. Okay, all right. So we'll again make notes here. We have done an experiment, we'll make notes, and this is the kind of behavior that we have to describe using our mathematical framework. Okay. So this is what we said. Electron behaves in different ways depending on whether we are looking at it or not. If you are looking at it with the camera, it behaves nicely. If you have a camera here, it behaves nicely, and it either goes to slit 1 or to slit 2, no problem. Right? If you are not looking at it, they behave weirdly and go through both slits at the same time, giving you the interference pattern. Okay, so our conclusion is this: electron has to be in slit 1 and slit 2, every single electron. Okay, when there is no camera, because that's the reason, that's how we explain the interference pattern here. Okay, but it's in slit 1 or slit 2 when observed. When you observe, it's either in slit 1 or slit 2. Okay, now let's make a number of measurements. It's a thought experiment, and we'll say that the probability is 50-50. Okay, or 50%, that the experiment is set up in such a way, or in the given experimental setup, we see the electron 50% of the time in slit 1 and 50% of the time in slit 2 when we try to understand in which slit it is. Alright, so this is experimentally measured quantity. Let's just say in our experimental setup it is 50%. Alright, so the mathematical framework of quantum mechanics must describe the above behavior and predict the probabilities for measurements. Okay, so we need different things happening here. It needs to, the mathematical framework needs to include superposition. Okay, it should be able to predict the probabilities. Okay, there should be something in the mathematical framework that gives us, that allows us to calculate the probabilities. For example, this 50-50, the theory should predict that you should get 50-50. And third thing, alright, this may not be included in the mathematical framework, but it should tell us what happens when you make a measurement. Okay, so when you are looking at the electron, it's never in superposition, it's always in one of the possible states. So the theory that we are trying to construct should take into account of all these three things. Okay, because this is the way nature behaves. We look at nature, and our job as physicists is to describe nature the way we see it in experiments. Okay, so we do so many experiments, we are describing the experiments using a mathematical theory. You may start asking why this happens, why does the electron behave like this? The answer is I don't know. Okay, I don't know why the electron behaves like this. Probably nobody knows why the electron behaves like this. We just know that this is the way electron behaves. Okay, so we have done the double slit experiment. Alright, so as I said before, we need, the main ingredient is superposition. Alright, which means that in our mathematical framework, we need objects. Okay, we need mathematical objects. When we make a mathematical framework, we need mathematical objects that behaves like electrons. And what's the main behavior of electrons? If the electron is in slit 1 and slit 2, okay, then it's also in both slits at the same time. Okay, this is the behavior of an electron. Right? If this is a possible state and this is a possible state, then this is also a possible state. Okay, now if you are familiar with some mathematics, you remember that this sounds like vectors, right? If you, for example, if you take three-dimensional vectors, if you take R1 vector and R2 vector, you see that it's another vector in the same space, right? Alright, so if you take two vectors and you add, you see that it's another vector in the same space. Right? This sounds like an electron. Why not vectors? Why don't we use vectors? Because here, if this is a possible state and this is a possible state, the superposition is also a possible state. Here, if you have this is a vector, this is a vector, then the superposition is also a vector. Okay, so this is similar, right? Why don't we try to describe electrons, or why don't we try to represent electrons using vectors? Because they seem to behave in the same way. Okay? There's a problem here because if you use three-dimensional vectors, the three vectors as you call it, the three vectors, okay, which means that it has three components, I, j, k are the bases, etc. If there are three vectors, if you are talking about three vectors or three-dimensional vectors, there are only three independent vectors, three independent directions, okay, three independent states. Okay. So you can only account for three independent states if you are taking vectors. This sounds like vectors, and this is a good guess. Okay. Okay, this is one state. Okay, so you see that the behavior is very similar. Okay, you see that the behavior is very similar, but we cannot choose this because this can have only at most it can have only three independent vectors. Okay, but we need to describe electron with a definite position or which is at a point, etc. And each point is independent of each other, and we may have infinite points. All right, if you take space, there are infinite points on it. Okay. So you need a vector space. So you need some kind of vectors with infinite independent vectors, with at most infinite independent vectors, because each position is independent, right? And electron can be in different positions at the same time. So you need a kind of mathematical construct similar to vector space, which allows infinite number of independent vectors, because we need to, that's the kind of behavior we need to describe. Okay. And then you look at some mathematics textbook. Okay, you take your Afghan, right, mathematical physics by Afghan, and just go through it. You will see that there indeed is a nice mathematical framework like this. It's known as linear vector space. It's known as linear vector space. Okay. It is a generalization of the ordinary vector space that I talked about. All right. It can be considered. It can be considered. I'll call this as LVS, all right, linear vector space. You can take a mathematical textbook or some mathematics textbook, and for no reason people have invented this mathematical framework. Invented or discovered, I don't know. But in mathematical framework, you will see that this mathematical framework already exists. Okay, and you can understand it as a generalization of the ordinary vector space that I talked about, and there are two generalizations. All right, there are two directions in which the generalization comes. The first idea is that we allow the scalars to be complex numbers. Okay? Because, for example, if you take this vector a, let's say r vector is equal to xi plus yj plus zk. Am I right? Okay, and we can write it also as a column matrix x, y, z. And what are these? These are real numbers. These are real numbers. Okay, these scalars, the scalar quantities in real vector space are real numbers. And this I, j, k we call as basis. Right? This I, j, k we call it as a basis set. Okay, this is the basis in terms of which we expand all the vectors. So all the vectors in three-dimensional space can be expanded in terms of three basis vectors. All vectors can be written. A vector is equal to, let's say, axi plus ayj plus azk in three dimensions. All right, and these are real numbers, and we call the set ijk as the basis set, okay, or basis vectors. All right, and in linear vector space, these numbers are no more real, it can be complex. Right? We allow these numbers to be complex numbers, and we do not restrict ourselves to three dimensions. There can be infinite dimensions even. Okay? So this is linear vector space. It exists even before quantum mechanics. Linear vector space already exists in mathematics before quantum mechanics even came to existence. Okay? So we'll try to make this correspondence a bit more concrete. Okay. So I want you to understand there is no logical reason why this is the correct mathematical framework. Okay. So the thing is that we make a mathematical framework, we construct a theory and see if the predictions are correct, and we make predictions and check if the predictions are correct. All right. The reason why we choose this mathematical framework ultimately is because it works. Okay. That's the only reason. There is no other logical reason here. There is no really logical reason to choose linear vector space. But you just try and you see that it works, the correspondence works. There is no other logical reason for that. Okay. Ultimately, the theory that you construct has to describe nature, that's all. Okay. Now, let us look into vector space. Okay. A vector space consists of a set of vectors together with a set of scalars which is closed under two operations, vector addition and scalar multiplication, which means that if you add two vectors, you will get a vector in the same space. If you multiply it with a scalar, you again get a vector in the same space. It does not take you out of the vector space. So, by vector space, you do not have to think of the three-dimensional space. No. In mathematics, space means it is a set of points. It is just a set. It is just a mathematical set. Okay, it is a set of objects. Right? It is a set. It's just a set. You don't have to confuse it with the real three-dimensional space. Okay, that's still there. It's not gone. This is a different kind of abstract space. Okay, it's a mathematical set. Now, the scalar mentioned are ordinary complex numbers, and closed. What do we mean by closed? That it means that if you do these operations, it will never carry you out of the space. So, if you have a set, you take two elements in the set and you multiply by a complex number or add, it will again remain inside this set. Okay, that's what we mean by closed. And there is a nice symbol, okay, to represent the vectors. This is, we put a number or a symbol inside an angled bracket. Okay, this is a notation that will follow. It's known as the Dirac notation. It's known as the Dirac notation. Okay. Dirac notation. So in Dirac notation, we represent the vectors in linear vector space by an angled bracket, and inside angled bracket could be a symbol or a number, anything. Okay. Now you will see that it's not surprising. Okay, it's not a coincidence that we chose to write the state of the electron like this. Okay, electron in slit 1 we wrote it like this. Here this was the notation for vector. Okay, and there's a reason why we used the same notation, which you will see soon. Okay. And closure under addition means if you take two vectors, add them, you get another vector in linear vector space. Okay, you take two vectors and add, you get another vector in linear vector space. Okay. So the property of closure under addition and multiplication by scalars, let us construct vectors which are linear combination of other vectors. So if you have two vectors, alpha and beta, okay, you can construct a third vector by this rule, A alpha plus B beta is also a vector. Okay, so given two vectors, you can construct more vectors like this. This is known as superposition. All right. Now you compare. So that means if alpha and beta are vectors in linear vector space, then so is this. This is also vector in linear vector space. Now compare it with what we said earlier. If S1 and S2 are possible states of the electron, we said earlier the principle of superposition. If S1 and S2 are possible states of electron, then a superposition of them is also a possible state of the electron. We said this. Okay, and here we are saying if alpha and beta are two vectors, then a superposition of them is also a vector. All right. So these are two different things. This we made from experiment. This is from the mathematical framework. They sound very similar. Okay. So why don't we just make this identification? All right. So we'll make this identification. So we just compare these two statements. They look very similar. Let's just say, all right, quantum mechanical states can be represented by vectors in linear vector space. All right. Because of the similarity, we are just trying this possibility. All right. We are trying this possibility that quantum mechanical states can actually be represented by vectors in linear vector space. Okay. Now the vector space in which the quantum mechanical states lives is known as the Hilbert space. We won't go into the definition of it right now. We'll be doing it in future classes if time allows. Okay. You just remember that Hilbert space is just a subset of linear vector space. Right. So the linear vector space that describes quantum mechanical systems or quantum mechanical states is known as the Hilbert space. I want you to remember this as a word. I want you to keep this word in your mind. Okay. And the state space of quantum mechanics is called the Hilbert space. Hilbert space involves vectors. Okay. Hilbert space involves vectors. Right. So the state space of classical mechanics was known as a phase space. Okay. The state space of quantum mechanics is called the Hilbert space. This means that all the elements in a Hilbert space, okay, all the vectors in Hilbert space corresponds to a possible state of a quantum mechanical system. This means that all vectors in Hilbert space is a possible state, represents a possible state of the electron. Okay, this is what we mean when we say that the state space of quantum mechanics is called the Hilbert space. Okay. All right. So to conclude, in mathematical formulation, vectors in linear vector space corresponds to possible states of the quantum mechanical system. The possible states of the quantum mechanical system corresponds to vectors in Hilbert space. This identification lets us incorporate the principle of superposition in a beautiful way. Okay. So the first thing that we wanted to include in our mathematical theory is the principle of superposition, and we have achieved it by choosing linear vector space. All right. We have achieved the representation of superposition principle by choosing the mathematical framework of linear vector space. Okay. All right. But that's not all. In classical physics we have states. Okay, and state is the position and momentum. There is nothing surprising here. But now we are saying that state is some abstract vector in some abstract space. All right, abstract vector in abstract space. Now, how do we extract measurable quantities? Okay. Suppose I know that the state of the system is represented by a particular vector in the Hilbert space. Okay, so the theory has to answer the following question. Right? If the electron is represented by this state and you measure the energy, what value will you get? right? If you measure the energy, what value will you get? Okay, so these measurable quantities are known as observables. Okay. Energy, momentum, spin, polarization, all these are examples for observables. Position are all observables. All right. We have the state. All right. How do we represent observables? All right. So we look into linear vector space and you see that there are other objects called as operators. Okay, there are other objects called operators. You might already be familiar with the word operator. Okay, so mathematically an operator defines a relation between two vectors. An operator defines a relation between two vectors, all right, which means that an operator acting on a state generally changes it into another state, all right. And in this equation, this a cap with the hat, a hat, is called an operator. The vector beta is obtained by acting a cap on vector alpha. All right. Now I'll give you two examples for this. All right. For vectors in linear vector space, you will have, for example, column matrices. Column matrices. Okay. If you look at column matrices, you will see that it follows all the axioms of linear vector space. So you can say that column matrices form a linear vector space. Okay. Also complex functions. Functions like f of x, which are complex, let's say f of z. Okay, complex functions, let's say f of x. All right, this means not f of z, it's not f of z, it's f of x. Okay, which means that corresponding to each x, this function gives you a complex number. Okay, so I'll give you two examples now. I'll give you two examples for linear vector space. Okay, the first example is the column matrices. You will see that it obeys all the so there are some elements here, all right, all the properties of a linear vector space. Another is a complex function like f of x or f of x comma y comma z or f of r vector. Okay. This means that this complex function spits out a number. If it spits out a complex number, all right, if you give a number here for x, it could be a position, for example, and it gives you a complex number of the form a plus ib. So associated with every point in space, you have a complex number. That's an example for a complex function. Okay. So it's easy to see that complex functions as well as column matrices, right? Column matrices behave or they construct vectors in linear vector space. All right, it follows all the properties of linear vector space. Okay, so two examples, column matrices and complex functions. All right, and an example for an operator is even simpler. You know that if you have a column matrix, okay, if you act a square matrix on it, you get another column matrix, right? You get another column matrix. So you'll call this as A, this is some square matrix which I call as M, and this is some other column matrix which is known as B. All right. So if you multiply a column matrix or column vector, as someone might call a column vector, by an n by n square matrix, you will get another column matrix. All right. So this is an example for an operator. Okay. In the case of complex functions, you know that if you have a differential, if you differentiate, this is an example for an operator. In the case of complex functions, this is an operator. Why? If you take some function, let's say x square, and act upon it and act an operator on it. Okay. So if you take a function, a complex function or a real function, if you take x square and do d by dx, you will see that you get a different function of x, which is 2x. Am I right? If you take d by dx of x square, you get 2x. Okay. You see that x square is a different function from 2x. Okay. So this is an example for an operator, because you take one vector, this is an example for a vector, you take one vector, act an operator on it, you get another vector. Or if you take one function, act an operator on it, you get another function. So differential operators are examples for operators. Also square matrices are examples for operators. Okay. You can say these are two different ways of representing an operator. Now you might have already guessed that this is the reason why there were two formulations of quantum mechanics. Right. One way to represent an operator is by matrix, okay, and a vector by a column matrix. Right. Another way to represent a vector is by a complex function, and then the operator would be differential operators. All right. So if this representation is used, it's known as wave mechanics, and if this representation is used, exclusively. It's known as Heisenberg's matrix mechanics. Right now we know they are all part of the same theory. All right. So we have found another object. We said that states are represented by vectors. States are represented by vectors, and we look how do we represent observables. We say that all right, there are other objects here which are called operators. Let's try representing observables by operators. All right. So that's the next part that we have. Observables like energy, momentum, position, spin, etc. in quantum mechanics are represented by operators that act on state vectors. All right. Operators that act on state vectors. All right. Okay, all right. Now there is another problem. Okay, we can actually measure the values of observables. We can measure the energy, we can measure the momentum, we can measure the position. These things can actually be measured, and what we get are not matrices, what we get are real numbers. Okay, what we get when you make an observation, when you make a measurement of an observable are real numbers. Am I right? You measure an energy, you get a number. You measure the momentum, you get a number. You measure the position, you get the number. Okay, these are real numbers. Not any matrix or d by dx. We don't measure d by dx. All right. So we have got energy, momentum, position, which are all measured as real numbers. You get a reading on some kind of apparatus. It's a real number, right? We never measure a matrix or a differential operator. Okay, so that's fine. So what do we do now? We need some real numbers. We need to associate some real numbers with these states, with these vectors, and these operators. Okay, we need to associate some real numbers. And then the only option, all right, there are not many options there. We already took vectors for states, we took operators for observables. Then now you need some real number associated with these things, and what you have is eigenvalues. What you have is eigenvalues. So and this is known as an eigenvalue equation, right? So some operators, when it acts on a state, right? I said earlier that you get a different state when an operator acts on a state. You get a different operator. You get a different vector when an operator acts on when an operator acts on one vector. You get another vector generally. All right. But for an operator, if you take an operator, let's say a cap, there are some special states. All right. There are some special states which give you, when the operator acts, it gives you exactly the same state. It doesn't change the state, multiplied by some number. Okay, multiplied by some number. This is also there. Okay, so there are some special states corresponding to an operator. Okay, and when the operator acts on the special state, it does not change the state. It gives you exactly the same state multiplied by a number. All right, and this case we call this equation as an eigenvalue equation. Eigenvalue equation. Okay, which means that operator acting on the state gives you a number multiplied by the same state, same vector. All right. So I am already using state and vector interchangeably. The word state and vector interchangeably. All right. It is known as an eigenvalue equation, and in this terminology, we say that alpha is an eigenvector of A with eigenvalue small a. All right. So alpha is the eigenvector of operator A corresponding to the eigenvalue small a. Right, that's the terminology. So we have got numbers here, but we have a small problem. These numbers, all right, these numbers, because we are talking about linear vector space and operators over there, these numbers are complex. These numbers are complex. Okay, they can be imaginary. There can be an imaginary part. But when you measure an energy or a momentum, it's never complex. It's always a real number. All right. This only means that we cannot take all operators as observables. We can take only those operators. All right. So we'll just identify. We'll try to make the identification that eigenvalues are the measured values. Okay. We'll try to make the identification that measured values are actually eigenvalues. All right. But there's a problem. Eigenvalues can be real or complex. This means that we cannot take all operators as representing observables. It means that we can only take those operators, whose eigenvalues are always real. Okay, so if you want to represent the measured values by eigenvalues, you should take only those operators whose eigenvalues are actually real. All right. So we conclude that all operators cannot represent observables, only those with real eigenvalues. All right. So we can choose only those operators whose eigenvalues are real, and such operators we know from, if you look at the mathematics textbook, you know that there are a class of operators called Hermitian operators whose eigenvalues are always real. Okay. All right, so this is what we mean, Hermitian operators, eigenvalues are real. So now we make this correspondence a bit more concrete. Earlier we said that quantum mechanical states are vectors in Hilbert space. We'll put a double-headed arrow. All right. So corresponding to every quantum mechanical state, you will have a vector in Hilbert space. Corresponding to every quantum mechanical observables, you have an operator, but not all kinds of operators, but specifically a Hermitian operator. Alright, so earlier I said that observables are represented by operators. I'll make it a bit more clear. I'll say that observables are represented by Hermitian operators. Alright, and measured values corresponds to eigenvalues of Hermitian operator. Alright, so we just try this side. We just make this identification and we see. We try. Alright, we make predictions using this kind of mathematical formalism, and we check. Alright, we check it with experimental results, and we see that it is good, it works. Okay, and ultimately this is the reason why this mathematical framework is used. No other reason. Alright, it's just that it works. Alright, so this correspondence works because it makes predictions, correct predictions. So this I call the correspondence between nature and mathematics. On one side you have got nature, there are quantum mechanical states, etc. And on the other side you have got mathematics. So you see that there is a nice correspondence between nature and mathematics, and as I said earlier, it works. Okay, and it works to that extent that people used to say that, or people say that mathematics is unreasonably effective. All right, it was Eugene Wigner who said that mathematics is unreasonably effective. We don't know why mathematics is so effective, but it all works, unreasonably effective. Okay. So we have described quantum mechanical state. We know how eigenvalues are there. Quantum mechanical observables are Hermitian operator. One thing that we missed out is probability. Okay, one thing that we missed out is probability. We also need to predict the probabilities of measurement. Right, and that also can be identified using this thing that we will be doing in the next session. Okay. All right, so I think it's time to wind up for today. It's really interesting. There's a lot more to discuss in this, but our time is up. And I thank you all for attending the class, for attending this lecture. I hope you enjoyed it. If there are any questions, you can ask. The Google Meet link for discussion will be in the comment box. Okay, thank you all.